Good morning, friends. My name is CH Srinath. I am from CSCF section. My course name is Applied Physics. Today's topic about direction and planes in crystals. Introduction to crystallography. Crystallography is a study of crystals and their structures. It examines how atoms are arranged in a crystal lattice. Understanding crystallography is essential in material science and chemistry. What are crystals? Crystals are solid materials whose atoms are arranged in a highly ordered structure. They can form through natural process or be synthesized in labs. The unique arrangement of atoms gives crystals their distinct properties. This is a crystals. Crystal lattice. A crystal lattice is a three-dimensional arrangement of points that represent atomic positions. Each point in the lattice corresponds to one or more atoms in the crystal. The arrangement can vary widely, leading to different crystal structures. This is a crystal lattice. Unit cell definition. The unit cell is the smallest representation with unit of a crystal lattice. It contains all the information needed to construct the entire crystal. Unit cells can be categorized based on their shapes and dimensions. This is unit cell definition. And next is a Miller indices overview. Miller indices are a notation system for identifying crystal planning planes. They are represented as a set of three integers h, k, l. Miller indices help in describing the orientation of crystal faces. These are Miller indices overview. Determining Miller indices. To determine Miller indices, identify the intercepts of the plane with the axis. The intercepts are then used to form the reciprocal values. The resulting values are simplified to the smallest integers. These are the determining Miller indices. Crystal directions. Crystal directions are specified using a notation similar to Miller indices. They describe the orientation of a particular vector in the crystal lattice. Directions are denoted using square brackets. Example U, V, W. These are the crystal directions. Vector representation. Vector representation. A vector in a crystal direction is represented as U, V, W. These components indicate how far the vector extends along each axis. Vector representation is crucial for analyzing defects and dislocations. These are the vector representation. And next is a planes versus directions. These are important thing. Planes and directions are interconnected but represent different concepts. Planes refer to two-dimensional surfaces while directions refers to one-dimensional vectors. Both are essential for understanding crystal symmetry and properties. These are the planes versus directions. And next is the importance of crystal planes. Importance of crystal planes. Crystal planes play a significant role in determining the physical properties of materials. Crystal planes play a significant role in determining the physical properties of materials. They affect how crystals grow, cleave, and interact with light. Understanding crystal planes in critical for applications in electronics and optics. Understanding crystal planes in critical for application in electronics and optics. These are the importance of crystal planes. Importance of the crystal planes and types of crystal systems. What is the types of crystal systems means there are 7 different crystal systems in crystallography. Each system is defined by its unique unit cell geometry. The systems include cubic, tetro, orthohorbic and more. Uh, these are the types of crystal systems. What is means there are 7 different crystal systems in crystallography. Each system is defined by its unique unit cell geometry. The systems include cubic, tetragonal, orthohorbic and more. And next is the cubic crystal system. The cubic crystal system features unit cells that are equal in all dimensions. Examples include sodium chloride, NaCl and diamond. Cubic structures exhibit high symmetry and are often used in electronics. Cubic structures exhibit high symmetry and are often used in electronics. Hexagonal crystal system. Next is the hexagonal system has a unit cell characterized by a hexagonal base. An example is graphite, known for its layered structure. Hexagonal crystals are significant in application like batteries and lubricants. These are the hexagonal crystal system. And next is a analyzing crystal symmetry. Analyzing crystal symmetry. Crystal symmetry refers to the orderly arrangement of atoms in a crystal. Symmetry influences a crystal's physical and chemical properties. Techniques like X-ray diffraction are used to analyze crystal symmetry. These are the analyzing crystal symmetry. And Brave's lattices. Brave's lattices are distinct arrangements of points in space that form a crystal. There are 14 unique Brave's lattices classified based on symmetry and dimensions. Each lattice corresponds to specific types of crystal systems. These are the Brave's lattices. Twinning in crystals. Twinning occurs when two or more crystal segments share a common orientation. It can affect the optical and mechanical properties of crystals. Understanding twinning is essential in mineralogy and materials science. These are the twinning in crystals. Defects in crystalline materials. Defects can occur in crystals, impacting their properties and behavior. Common defects include vacancies, interstitials, and dislocations. Studying these defects is important for improving material performance. Applications of crystal directions and planes. The understanding of crystal direction and planes is vital in various industries. Applications range from semiconductor manufacturing to pharmaceutical. Innovations in nanotechnology also rely on precise manipulation of crystals. Future direction in crystallography. Advances in technology are paving the way for new discoveries in crystallography. Techniques like electron microscopy and X-ray sources are evolving. Future research in will focus on new material and their applications. Next conclusion. Last is a conclusion. Understanding directions and planes in crystals is fundamental to material science. The study of crystallography has profound implications across various fields. Continued research will unlock new potential in technology and materials. This presentation covers the essential aspects of directions and planes in crystals suitable for an academic or professional audience. Thank you guys.